All right. So now finally the ultimate example here. So that's kind of like the level that we can see on our fourth exam, right? So in terms of the nomenclature, if you are curious. So here we go. So like we have again our substituent, right, which is going to be looking like this. So this is ethyl, right? And then the acid will be a little bit more complicated, right? Because it's going to be not just kind of like a completely straight chain or aromatic acid, right? We have had two kinds already, if we think about it, but it's going to be the one which has the substituent, right, on it, such as bromine. So still we can like see that we have an ester. Okay, great. We can start with the substituent in yellow, right? So let's put down its name. It's going to be ethyl, right? So then we'll have the space. Then we are going to have also O8 as our suffix. So this is good. Now finally the acid, right? So now what kind of acid is that? So we are going to have 1, 2, 3, 4 carbons total, right? So, but here we need to do a little bit of the numbering, right? So this is going to be carbon number 1, 2, 3, 4 in the respective acid, right? If we just imagine the acid in green. So then, and then apparently on carbon number 3, there is a bromo, right? So it's going to be technically, if you just think about the acid name, 3-bromo butanoic acid, right? So then to name the respective ester, we just need to retain 3-bromo butane and remove oic acid part, right? So, and then here we go, right? So it's just going to be like pretty straightforward. 3-bromo, so 3-bromo butane O8, right? So that's it. That's where we kind of like how we build our name for these complicated looking esters. So that's pretty much kind of like followed our rules, right? So then we apply the same even color scheme, right? So if you think about it, to name those esters. All right. So now let's say we're going to move on finally to like physical properties of the carboxylic acids. So at this point, after all our kind of exploration and review of the general chemistry, right? So you should be able to like recall that the carbonyl is a polar group, right? So, and the carboxylic acid group will also be polar, right? So you can also think about the partial charges, right? So that's kind of like a natural ramification of all that stuff. So, like for example, oxygen is more electronegative than hydrogen, right? So we'll have the delta minus and then delta plus conceivably. If you think further about that, so some people did show the dissociation or ionization of the acid in the past, as on Tuesday, right? So then upon dissociation, they were showing, okay, the acid would produce H plus, it's one of the ions, and the respective counter ion or anion, right? Such as HCl will produce H plus and Cl minus. Same thing will apply to the carboxylic acids, right? But of course, structures will be different, right? So you need to kind of like think or see what you are working with. So then what else? If you look at the carbonyl group, right? So also carbon will be less electronegative than oxygen, right? So, and we can potentially put the delta plus charge here, delta minus here, right? So that's kind of like what we are going to deal with, and then it potentially will be useful for us to show the hydrogen bonding, actually, so between certain molecules. So yeah, and like conventionally, there is a like map, right? So that shows the charges. So that's how it will look like, right? So basically, like the green and red colors are shown to kind of like signify the concentration of those like partial negative charges, right? So, and then, yeah, so they will be kind of like color coded. But for now, so like we need to think about the differences in electronegativities, right, between carbon and oxygen, and then between the oxygen and hydrogen. So these are the kind of subregions we're going to look at. So because, why? So because they will help us understand how the like interaction will happen, for example, for activity number 1, right? So it's very applicable here. So from theory to practice, right? So you always need to like try to do that. So because otherwise, like, why do we like learn that, right? So there could be various reasons. but one of them is like from like theory to practice. So, and then basically here what you need to think about is the electrostatic attraction a lot of times, right? So because the positive and negative charges will attract according to your like physics background. So then let's see. So in terms of hydrogen bonding, right? So now we go from like a single molecule to apparently several molecules. So the what's it called? The carboxylic acids can form the dimers, right, with one another in the following fashion, right? So basically, you are going to draw one molecule of the acid like so on the left side, on the left-hand side here in this so-called dimer. Dimer means basically two pieces, right? Two things together, dimer. So just like we had polymers, it's like a lot of like poly things connected together, right? So here we have only two parts connected together. So the first one will be like carboxylic acid drawn as such, right? In which case the carbonyl will kind of point up and OH will be pointing down, right? So then you will have the other acid, which will be kind of flipped, right? Quite literally. So, and then the carbonyl will be pointing down, the OH will be pointing up. And then this arrangement will just be convenient to show the like hydrogen bonding, right? So which will exist between the OH of between the hydrogen of the hydroxy part of the acid, right? So because hydrogen will have the partial positive charge, as you can see from the scheme, like right here, right? And then it will be very conveniently located next or opposite to the oxygen, the carbonyl oxygen, right? With the delta minus. So they will attract. So the same thing exactly will happen here, if you think, but it's just flipped, right? So delta plus, delta minus will interact. So, and then you have the hydrogen bonding here. So because you have this kind of like appearance or whatever the appearance of the delta minus delta plus. And also the very important requirement, you have the polar bond, right, between a certain atom and the hydrogen, right? So typically we need to have something like HF, NH, and the OH. So that's what we look a lot at, right, in terms of hydrogen bonding. So you see they kind of all go together in the periodic table like NOF atoms. So it's pretty convenient to think about. So yeah, and then here you have it, right? So the requirement for the hydrogen bonding is fulfilled. So you have like opposite charges, partial though, but still opposite. So that's number one. Number two is that you have this OH bond, which is highly polar and can generate delta plus, for example. So, and then, yeah, it will connect with the kind of like delta minus on this carbonyl oxygen. So then because of that, so like if you recall your Gen Chem experience maybe, right? So the water can do the hydrogen bonding. That's why it has a relatively high boiling point, like 100 degrees Celsius, right? So, but for example, if we look at, bless you, like ethers, right? So that's our new kind of organic compounds. So they don't do hydrogen bonding. So they boil at very low temperatures, maybe like 40 Celsius, right? Much lower than 100 for ethers. So, but for the carboxylic acids, so here we go, very high boiling points apparently, and because of this hydrogen bonding situation. So now just some statistics here. So where are we? So here we go, right? So this is our comparison, right? So if you look at, for example, like whatever is not capable of hydrogen bonding, it's like very low boiling point, 35 Celsius, right? So like ethers are comparable actually in terms of boiling points with alkanes because they cannot do the hydrogen bonding, right? So, and even though there is this oxygen present, but it's only one basically polar atom, right? So that will provide some polarity and difference in electronegativity. So, but it's not going to be like enough to make like a highly polar molecule, right? So that will generate lots of like positive and negative charges, right? So then once we go to 1-butanol, so here we can have maybe like dipole-dipole interaction at best. When we go to the oxygen, when we go to the alcohol, then apparently, so we will make the hydrogen bonding, right? So which is stronger bonding-wise in the hierarchy of intermolecular forces, and you'll have a substantially higher boiling point for a comparable size alcohol molecule, right? So then you'll have a little bit smaller boiling point for the butanol, right? So which is the aldehyde, because aldehydes, according to exam 3, cannot hydrogen bond with one another. It was one of the true-false questions, right? So then it's going to be like a little bit lower boiling point, right? But we still have the kind of like here the carbonyl group, which can provide the like dipole-dipole interactions, right? So, and then what else? Then we have the propanoic acid, which will have a huge boiling point here. So, and if you think about the like oxygen, alcohol, right? So you'll have like one alcohol molecule making another maybe hydrogen bond with another alcohol molecule. Let's do the same alcohol here, just for the sake of the example. 1, 2, 3, 4. So that's our 4 carbons. Then we are going to have the oxygen here and the H, right? So then we can show the hydrogen bonding like so. So that's the one, right? So you're gonna have delta plus on H, delta minus on the oxygen, and then here it is. It's your purple. It's a little bit kind of like screwed up here, so I should have aligned them better. So, but kind of we still can trace the hydrogen bonding, right? So between two molecules, right? And it's only one dotted line. If you look at the acid, right? So you can show the dimer, right? So maybe using the propanoic acid as an example here. So because why not? So let's do that. So it's going to be 3 carbons total, right? So I'm going to have OH here and oxygen there. So it looks like I didn't miss anything. So now I'm going to do the hydrogen bonding event like this, right? So with the respective, what's that going to be? The delta plus here, delta minus, and the delta plus. So plus minus will attract, so very good. And then you have now 2 purple dotted bonds as opposed to just 1, right? So more bonding, then more strength, right? So they will be like stronger connected with one another. And then you have a jump, right? So from 118 to 141, if you compare alcohol versus the acid, because alcohol apparently will form only like one hydrogen bond, right? So between 2 of its own molecules, whereas the acid will form twice as much, twice as more, right, of the hydrogen bonds. So now, okay, so that's where we are. So that's just again some statistics here that the boiling points of the carboxylic acids, like of the comparable weight, let's say with alkanes, will be much higher, right? So then the boiling point of the respective alkane. So then aldehydes and ketones will be a little bit higher, right? So boiling point wise, if we look at the kind of about the same molecular weight of like 59 or something, right? So aldehydes, ketones, higher boiling point. Then primary alcohols will be like level 3, right? In terms of the highness of the boiling point. And then finally, top level, level 4, so will be carboxylic acids. So that's how they kind of like are arranged, right, in terms of their boiling points. It's just a trend, right, we need to be aware of. So that's again like more statistics here. So you can look at that if you want, just kind of like appreciate that table. I think it could be used for like some homework question. So just things like that, right? So we can see some sort of relationship, right? The higher the weight of the carboxylic acid, the higher the boiling point, right? So, but that's in some cases, so they will just decompose, right? When you try to boil them. So that's how kind of like the molecule decided to behave, right? So we cannot kind of like go to the infinite boiling point with the infinite molecular weight growth, right? So at some point, kind of like some trends will just like stop and then they will do something different, right? That's something to be aware of. So, and then oftentimes, if you are in your practice of like medicine, right? So then you can maybe like give only that much of like L-glutamine to your like patient or something like that. So until the patient like develops cancer, maybe, right? So like because glutamine is also good for the cancer cells, right? So in addition to just muscle growth, right? So then you need to like be careful here. Okay, we'll have some trend. We increase the glutamine and it's good for the muscle growth, but then it's too much glutamine and then like not so much of the physical activity, then you are kind of like done, right? And then you kind of start feeding cancer cells. So yeah, similar is true about the carboxylic acids, right? So the boiling point increases to some extent with the higher molecular weight, with the increase in molecular weight, but then it kind of like stops, right? So there's a decomposition happening. So then solubility is kind of like pretty straightforward here. So yeah, basically the smaller the molecular weight of the acid, the more it looks like water, right? So for example, if you have formic acid, it's almost like H2O. We can even see there is H2O and then there is CO added, right? Only two extra atoms. So if you look at this kind of stearic acid, which is present in like vitamins, for example, so as like one of the additives, so this one is not so much like water. Yes, there is like a H present and then oxygen, maybe another H, right? We can easily find it, but then there is like at least 16 more carbons. That's huge, right? Difference compared with just the like water molecule. So it's going to be not so much looking like water. It's more like an alkane, if anything, and then it's going to be insoluble, right? So we can like estimate. So yeah, just something to think about, like dissolves like. And then that's going to be helpful for your questions about miscibility, right? Who is miscible, who is not? Maybe explain why, for example, like let's say propanoic acid will be quite miscible, right? Infinite solubility in water, but palmitic acid is not like miscible with the water, right? So, well, you can use the kind of like structural argument. So now, so like maybe let's take a look at activity number 1, right? So it's a little bit of the build up, right? So we just try to like see if we can apply what we have gotten so far. So now we have an ester with water, right? So it's not the carboxylic acid with water, let's say, it's the ester with water. Somebody drew the carboxylic acid with water last Tuesday. So, I mean, this Tuesday, 48 hours ago. So that was quite nice. So, but now, what's that? What do we have? So we have the ester, right? Ester of your choice with 6 carbons, and then with the water molecule, it will form the hydrogen bonding, right? So let's try to give that a try. Yeah, so think about delta plus, delta minus distribution, right? So where they are at, and then how they can be aligned, right? So that's kind of a goal here. You can just like draw something, right? So then recall the polar bonds and make them go together. So let's say we have a candidate. Good job. All right. So let's see. We have enough paper here and everything. Okay, ester with water via H bonding. It's hydrogen bonding, right? In other words. All right. So take it away. So you have some colors here in the bin. And let's see what happens. Not yet. That's the chemical reaction. Sorry. So this only hydrogen bonding. Okay, so yeah, that's pretty good, right? So like the only thing we must not forget on the esters, so you need to put something on the oxygen, the other oxygen. This one will have, for example, so to make it methyl, to make it an ester, you need to have something that will be here, right? So what's going to be here? Maybe methyl, put just the methyl group there, right? So, and that's it. Now it's going to be proper, right? So because again, okay, all done. So awesome. Great job. So yeah, so we have like a nice possibility here, right? So that could be entirely the case. Just kind of again, don't forget the parts, right? So it's almost like you have everything for the ester except oxygen is literally kind of like lacking something, right? So and oxygen was lacking the methyl, right? So when you show this bond, also kind of like draw it this way. It's oxygen to carbon, right? So yeah, just make it straightforward. So not kind of in between or to the H, it becomes ambiguous, kind of like strange, right? So, but now, yeah, so good. Excellent. So yes, we can have the hydrogen bonding event. So delta plus delta minus interaction put into your pair between oxygen carbonyl and H, right, from the water. And then also, yeah, this also could make sense, right, because we have H plus. Good. And then we have delta minus technically on the oxygen here, right? So in our, what's it called? This kind of like the oxygen with the two single bonds, right, in the ester part. Okay, great. So yeah, that's well done. So we have blasted through that, I would say. So now we are moving on to the next. Should have done this at the very start. Okay, so now we are going to the next situation, which is going to be about the acid-base interactions. So now we're going to the reactions, right? Some people wanted to like show some reactions already. So here we go. So, and this is going to be like first what we started with is the acid-base chemistry, right? So what we need to know is essentially the ion exchange here, right? So like in the past, like you were able to dissociate some sort of carboxylic acid. Okay, so that's great. And then we were showing that how the acid can produce H plus and some sort of anion, right? So whatever that anion was. So now we're going to kind of like level up a little bit and then take a look at the reaction, right? So the so-called ionic exchange between the acid and the base, right? So that's going to be the goal here. So, and let's see. So for example, so you have, let's take a look. Okay, so you have some kind of like acid, right? Let's make it something more tangible. Maybe we are going to use 1, 2, 3, 4. Let's use the butanoic acid, right? So I think, yeah, it's one of your peers who did draw that, right? So maybe even several, actually. So you would have O minus and H plus, right? So those things will be created once the dissociation happens. But before it happens, you can show it just to kind of like keep track of the charges, right? So that's okay. So then you are going to use, for example, here, so we have sodium hydroxide, but I might as well try potassium hydroxide because of bananas. So that's like what we have here, right? So and bananas are good for you. So they're good for like whatever in the organism. So here we go. So we have O minus H plus, then we have K minus and I mean K plus and OH minus. So when they react, right? So now you need to predict what happens, right? It is just the ion exchange. So yeah, basically, so think about this situation. So generally, again, general examples, you have some kind of like AB thing reacts with, let's imagine it reacts with CD, right? So these are the chemicals, some kind of hypothetical chemicals. And now imagine that like hypothetically, again, A is plus charge, B is minus. C is plus charge, D is minus. So, and I tell you that you are going to produce a new combination of the ions, right? So, and then the requirement must be, so you need to have the new compounds, new combination, right? So new pairs, basically, of those charged species, letters in this case, but they also need to have opposite charges, right? So when they make new stuff. So now, what's going to be here, right? So this is the question here. So that's the question. What are we going to obtain? What's going to be the combination? It's going to be two new pairs, two new couples, right, of the letters that we are going to obtain. Let's actually look at this question. It's going to be here. So this question reaction kind of like two, right? So I'm going to go to this Google Classroom. That's going to be quite appropriate for this question. Okay, so what will happen, right? So what will happen here? So think about it and tell me, right? So you can just type, right? So what kind of products are you going to get from the reaction of AB and CD, right? So you need to do the exchange. Let's imagine these are ions, and you need to do the ion exchange, but in your new products, you must have the new combination of plus and minus, right? So these are the previous old combinations, AB plus minus, CD plus minus. So you cannot combine, for example, AC because they will literally repel, right? So that is against our rules. So AC will not happen, right? So BD will not happen either, right? So because it's like they will repel, they're both negative. So I pretty much like gave you all the options here. Now it's going to be about the like combinations, right? So it's like a puzzle or something, like Lego, whatever the analogy could be. So you might as well like approach it with the same thinking, right? So and then yeah, we can like transpond it to the like chemical reactions, right? So again, you have some kind of general principle, and then it's applied to specific situations. And specific situations could be like literally like thousands of, right? So we cannot physically cover them all, but we can take a look at the principle and then do our best here. So let's see. How's your energy today, by the way? Okay, so let's see what people say. All right. So, okay, well, we start in a negative fashion, but some people say it's good. Okay. So, all right. So, like sleep situations, all right. So, this is kind of an important thing for recovery. Okay, so and then people are good about hydrogen bonding. It's kind of like here, it's like very high energy going on in answers. All right, so all right, awesome. Very good. So now let's take a look at the next question. So it's going to be here, classwork. All right, so let's see what we have. All right, so lots of responses. Thank you for your effort here. And then we have, so what's that going to be? So, and then we have ADCB. Okay, great. So it's like almost unilateral, I would say. Great job. So you have AD because, so if you put together, right, them, so charges will stay on A and D. A plus, D minus. Okay, that's good, right? So they will attract. It fulfills our requirements. So then finally you have B and C. Let's put them together. So if we do that, B minus, C plus, they will also attract one another. So we are in a good shape, right? A, D, B, C. So now same thing happens here, right? So I'm going to like disconnect. So there is like an ionic bond between K plus and OH minus, right? And I'm going to like swap, right? So H plus, for example, like will be one thing that will go together. K plus, no, too bad, right? So OH minus will be our only option. So let's make it. And now you will see that it's going to be just kind of acid-base interaction, which has to yield the water as one of the products, right? So here we go. So HOH, like H2O, in other words, is produced, right? So then your other thing will be what? So we are going to redraw this part here, this huge anion. So, but it's fine. So you just need to redraw that. So there is like nothing like extraordinary. So and that's the one, right? So like maybe some people will show the lone pairs. Okay, that's like more power to you in this situation. And then it cannot combine with H plus because we don't remake the product, right? So, or the chemicals. So it cannot combine with OH minus. It was already used, at plus they would repel. Then the only other option is to put together K plus here. So that's actually what was done by Lucas last time. So, and then that's the one, right? So that's going to be your salt at this point. So imagine, so you have, for example, KCl, right? So K plus Cl minus, that's the salt situation. So, but in this case, you have K plus, and then this kind of like other anion that was derived from an organic acid, which is also okay, right? So that's it. So this is going to be like your situation that will take place, right? When you have the reaction between the carboxylic acid and some sort of inorganic base. So it's going to basically, scope is pretty narrow for us, KOH, because of the, like, again, bananas contain K plus, potassium, right? So sodium is contained somewhere else, right? So like whatever, like multiple food products. If we go down this route and then, yeah, so we are going to form the salt and the water, right? So in terms of the naming, right? So it's going to be pretty straightforward. Again, you need to look at this like, for example, you have sodium chloride, right? So in this case, you are going to have also the same kind of like sequence, right? Sodium, right, is going to be the name of the cation, goes first, right? So then you have some kind of a general carboxylic acid. The salt is going to be carboxylate, right? So the general name. So, but here you have the sodium acetate. So why is that so? Because the acetate, right, so comes from the acetic acid. Acetic acid. So what is acetic acid? Acetic acid is just that. It is CH3, COOH. So it could be called either two ways, right? So basically our fundamental way is it is from ethane, so ethanoic acid, right? So it could be called ethanoic acid. Uh, ethanoic acid, right? So, but there is a conventional name, which is kind of actually more popular. It's going to be called acetic acid. So this compound here is also known as acetic acid. So that's kind of like, that's what mostly people use, acetic acid. So ethanoic acid is technically correct, right? It's by nomenclature. So, but it's like rarely used. So, but acetic acid, so for this compound, so is commonly used, right? So it's going to be methyl here, so COOH. So consequently, you can call it also sodium ethanoate, so that's fine. So or sodium acetate, right? So, but like most importantly, like figure out the ion exchange, right? So you have like all the tools here, and you can take it as a gift after the presentation and put it on your wall, like Hamza. So now let's take a look at some more examples, right? So here we go. So we can have the benzoic acid, right? It will also react with an inorganic base, such as KOH, could be sodium hydroxide. In this case, it is potassium hydroxide. Will undergo the ion exchange. Maybe for extra information, we can like show, okay, this bond will be broken and this bond will be broken, right? That's solid charges. There will be O minus and H plus. K plus, OH minus. So these are pretty much like staples, right, at this point. So that we kind of need to remember slash use from the general chemistry knowledge, right? So that's your like knowledge retention, which is kind of helpful. So, and then here we go, right? So OH minus exists as OH minus, right? So in the ionic form. It doesn't exist as like OH plus, for example. Same with the potassium ion. It exists typically as K plus, right? So it doesn't exist as a K2 plus, right? Or K minus. Some people do that. So they assign a negative charge to the potassium ion. Maybe it could be possible in some sort of like highly specific situations, right? So like with some sort of like radiation and such. So, and temperatures or maybe freezing temperatures. So, but for us, K plus is K plus, right? So don't make it anything else. Just kind of remember one route, and then it might as well be like easier for you, right? Just kind of like simplify things, maybe. That's one way to think about it. So now we have the salt, right? So most importantly, you need to be able to produce the result, right? So on the exam, so and then name it. So it's going to be potassium benzoate, right? So basically potassium, that's going to be our part here. So that's your potassium ion. So, and then benzoate, so comes from what? So comes from the purple part, which is provided by the benzoic acid. OH is gone, so now we have benzoate, right? Kind of looks like an ester to some extent, naming wise. So then, okay, so we have here more examples. So let's kind of like get to practice, right? So that's going to be kind of like nice. And we also have the activity, right? So activity number 2. Where is it? Okay, so found that. So we have activity number 2. All right, so that's your activity number 2 coming up, right? So maybe there are some people who want to still use the opportunities to show their work, right? So because why not? It is just redraw the same structures and then redraw like draw different structures, but the reaction will be the same, quite literally, right? So here we don't even have any like double charged ions, right? No calcium 2 plus or magnesium. It's all like mono charged ions, right? So let's take a look at some things here and see where we end up, right? So maybe we're gonna start with A, right? So if I'm gonna do A, so that's what's gonna happen, right? So let's take a look. So we're going to split this thing and this bond, right? So we will have the OH minus, sodium plus. Okay, we'll have a H plus with a plus charge and then sodium minus, right? So this is kind of like bad. All right, so now let's just kind of like draw on this piece of paper. It's going to be much better. So here I have, what's that? Propanoic acid, apparently, with sodium hydroxide. Okay, great. So let's do that. So that's your propanoic acid. So I'm actually going to like show the bond anyway. So, and then sodium hydroxide. Typically, ionic bonds are not shown, but for now, we'll just say, okay, well, this is going to be broken, right? This bond still, it's an ionic bond, still a bond, right? Between sodium plus and OH minus. And this one will also dissociate. So, and then you will make those charges, right? Then you are going to make a change, right? Maybe start with small parts. H plus will have to recombine with not sodium plus, they will repel, then OH minus, right? And here you go, you just start with water at least, right? So HOH, by the way, is the same as H2O, right? So it's a water, just written in a different way to emphasize that you have the connection between like H plus and like OH minus, right? So then next, what do we have? So now we are going to have this kind of guy, right? So that's going to be our anion. So like with the O minus. Okay, great. And now we just need to like find the coupling like partner, so to speak, right? So it's going to be not OH minus, it was already used, and then they will repel, right? But then the only other option is that, right? So now we made our salt, right? It's going to be sodium, 1, 2, 3, propanoic acid, sodium propanoate, right? So that's what we are going to have here, according to our naming of those salts. Okay, so now let's take a look at maybe like part B, right? So that could be like a little deceptive, but again, so you just need to kind of like look at what you can deal with, right? So that's kind of like how to describe it, I think. So we have this weird acid. It's called pyruvic acid. It's part B, pyruvic or pyruvic acid, right? So which will react with KOH. So same things apply. So this bond is broken and this bond is broken. So then we're going to have K plus OH minus, H plus, and then minus on the like what will become the anion from the acid, right? So you see like things kind of like repeat themselves. So it's like pretty good. So then we're going to show the reaction arrows. So again, here H and OH, almost like a no brain situation, right? So, and then it gives you potentially some kind of like at least partial points, right? So you show something like, as opposed to kind of not showing like anything, right? So some people like give up and then they kind of like don't do anything. So now we are going to have, okay, so that's going to be a little bit difficult, but it's fine. So we're going to continue, kind of the products will continue here. So down the line, and then I'm going to just redraw this strange anion like this. So everything gets like redrawn. So this is going to be O with a negative charge, and it has to combine with the K plus, right? So that's pretty much it. So now, yeah, other things. So like here, I'll just show you like what to do. Maybe like, of course, you are going to break this bond and this, right? So now it is just a matter of basically copying, pasting things and switching the ions, right? So some people say like ion switch, I say ion exchange, right? So doesn't matter. So you just need to like be able to like combine the make new combinations of the positive and negative charges, right? So they're like in the 1-to-1 ratio. So it's pretty straightforward here. So not so bad. So here, again, you will recognize that this bond will be broken and that one. So that's pretty much it. So now a little bit more of the build-up, right? So imagine what we had in the past was the ions that would contain multiple charges, right? And then it will be something like that. So let's say we're going to take a look at maybe, let's say calcium. So calcium hydroxide will be looking like this, right? So calcium OH2. So now imagine that it reacts with the HCl, and then we're gonna make the products, right? So similar things will take place, right? So we have this, but calcium is 2 plus. So now, okay, so what are we going to make, right? So what are we going to make? So we'll still have calcium 2 plus with something new, right? And then we are going to have H plus with something new as well, right? So now what's going to happen here? So I'm going to show you this something, and then this is going to be this 2 as a subscript, right? So, and then we're going to have also the stoichiometric coefficient of 2 in front of this kind of like product that will be made. Okay, so now maybe let's ask it to the Google Classroom. So here we go. So, and we have a question. Okay, so question, what will be made, right? What will be made? So here you need to use your knowledge of stoichiometric coefficients, right? Balancing chemical reactions and predicting the products. So, but again, so you are going to make the salt and the water, right? So because it is the acid, and then yeah, it's still a base, right? So just like there is KOH, so this one happens to have calcium, right, instead of potassium. So, and then you have calcium with a double charge, right? 2 plus instead of K plus with a single positive charge. So here we go. So you have calcium 2 plus OH twice, OH minus twice. And then you have H plus and Cl minus reacting with one another. So what will happen, right? So now that's going to be the question here. So this is there for a reason. It's like a hint for you, right? So because you need to remember that the molecules are neutrally charged, right? So if we have some kind of like double positive ion, right, whatever it might be, so maybe we have some kind of metal, let's say, with a charge of 3 plus, right? And we have an ion with a charge of X minus, we cannot just leave it as such and then go, right? So then we must have it like this, 3 plus, and now it is going to be 3x minus, right? So it's going to be 3 multiplied by minus 1 becomes minus 3. 3 and minus 3 becomes 0. So now it's proper. And same thing will apply here. I mean, in terms of just the reasoning, right? So you have calcium something, and then you have another product, right? So acid base will react. So what will happen? All right, so what will be made, right? So we have some responses coming in, so like good effort. All right, so let's see what we got. All right, so like people are working hard in the morning, so this is good news, I guess. All right, so we have, okay, great. So like a great knowledge of the previous chemistry. So it's gonna be unilaterally, people say calcium chloride. Magnesium, I don't know how magnesium happened to be here, so just like make sure that you are on the same page literally with everybody. So anyway, so it's going to be calcium Cl twice, right? So 2 multiplied by minus 1 becomes minus 2, and 2 plus, they will go together, become 0, right? So it's going to be, you can even put it here, like 0 charge. So, and now in terms of the water, right? So yes, you are going to have HOH, but you used to have 2OH originally, right? Consequently, you must have this like stoichiometric coefficient of 2. So now look at this. So you have still charge of 0, right? For the HOH, good. That's how it's supposed to be. And now you have 2OH, 2OH, right? You have here H and 2H. So now you need to put the stoichiometric coefficient of 2 in front of HCl and check again. Calcium, calcium. 2OH, 2OH, 2H, 2H, 2Cl, 2Cl. Great. So now we're in a good shape and we balanced our equation. So now let's continue to practice. Now maybe it's your turn. Somebody was mentioning magnesium, right? So very eagerly. So demonstrate how an aromatic carboxylic acid reacts with sodium hydroxide. That's one person will do that, and the other person will do magnesium. So it's going to be like quite challenging, but it is doable, right? So imagine that basically this is magnesium, and this guy, like Cl, is going to be your anion from this like huge carboxylic acid. So that's all we'll need to do, right? It's just a matter of drawing at this point and then making sure that the things are put on paper. So let's see what we have. So like maybe let's give way to some like new people, right? So let's start with A. Okay, so we have sodium hydroxide. So and then magnesium is still coming up, right? So that is gonna be on the table next. So maybe we'll be able to do magnesium as well. All right. So anyways, so that's yours, colors, and take it out. So that's the aromatic acid of choice. It's almost there. So we just need to do one more thing to make it an acid and we'll be in a good shape. All right, great. So that's just benzoic acid, right? So again, nobody prevents you from making it more complicated. You can put some kind of like isopropyl on the benzoic acid. So that's going to be like your choice as well. And now it reacts with sodium hydroxide, right? So NaOH. Yeah, great. So now, yeah, maybe you can show like which bonds will be broken, right? So you have like a bunch of different colors in the basket. Yeah. Or you can show the products, so which is also fine, as long as they are okay, then we'll be good. All right, so like a different color going on. Okay, good. Looks like it's purple. All right, charges, awesome. Well done. Okay, great. That's a salt. And then show also the byproduct, right? So what's the other molecule? So just to like balance it, right? Because it's kind of like easy work here. So, and your HOH. Okay, well done. So now, so does anybody want to try the one with magnesium? Okay, so like we have the candidate here. Okay, great. So now let's do magnesium. We're gonna switch to the beige sheet of paper. So looks like an octopus. And let's see what we have. So magnesium, maybe some, let's use a green color. So if you want to show the bonds. So, but it's going to be some stoichiometry action happening there. And also the like, subscripts, right? So it's going to be like pretty complicated potentially, but we'll see if we can make it. So it needs to be aromatic acid, right? So aromatic acid. So don't forget your double bonds. Okay, good. So then we have magnesium OH2. Awesome. All right. So now there's going to be some balancing happening, right? Here, don't forget your stoichiometry coefficient and the subscripts, right? So that's where we are. All right. Great. So magnesium will be 2 plus. Magnesium was 2 plus. It stayed, right? Not quite. It's going to be 2 plus. The charge is 2 plus. Put the 2 right in front of plus. Yeah, that's right. So, and then you will have, yeah, that's right. So you are going to have you need to double your ion, right? Double your anion. You have water, H2O. Okay, great. So now let's see. So we have one magnesium everywhere. That's good, right? So, but then magnesium is divalent. So you must have 2 anions. So put this anion into the brackets, the anion. Anion, negative charge, so that goes into the brackets. So it's like here, bracket 1 and bracket 2. Oh, yeah. Oh. Great. And now put the subscript 2 here. So that is gonna be it, right? It looks like magnesium chloride 2, right? So but with the 2 anions. So now how many waters do you have? So you have 2 OH, 2 OH. And now you have 2 anions. Then you need to have 2 acids as well. So that's it. So that's your situation. And now you can take a picture of that, right? So you can talk to Brian about that situation. So, but literally all it is, imagine that instead of H with this carboxylic acid stuff, you have HCl. And now this is going to be your Cl minus ion. Same thing. You literally have just a different picture, right? Instead of like small Cl, you have a huge drawing. So that's all it is. So also for just like other exposure purposes, you can call it X, just X, right? And you have 2HX, and then this guy here will be like in the brown circle here. It's going to be X as well, right? So you have magnesium X2. So that's all it is, right? Basically, if you like think about it, so like you just need to draw other things, right? Instead of like X. So, but it's not so bad. So then, yeah, as you do like several examples of that kind, it's going to be not so much time consuming. So yeah, you'll be like in a better shape. So it's completely trainable, so to speak. Okay, so we have done a good job, I think. So now, what else? Okay, so we are going to move on to like future chemical properties. So let's see, let's start at least the carboxylic esters, right? So these are esters. So like there is like another piece of trivia. So is that esters can be used a lot as aromatic agents, right? Not as in like aromatic group, but they kind of smell well, right? So they could smell like bananas, for example. That's the one which I made back in the day when I was in the undergraduate program, right? So that was our synthesis. I think it was literally lab one, make an ester, right? All of a sudden. So that's how it went, the introductory chemistry for me, or organic chemistry one, lab one. So then other things can be used like as a nail polish remover. So that's like pretty useful, right? So if we think about it, so now let's take a look at how they are made, right? So apparently, so like when we look at the chemicals of sorts, we need to think about how they can react, just like what your peers were showing now. So that's their reactions, right? But also we need to like think about how stuff is made, right? So apparently esters are made, so that's why we're thinking about last time. So how to approach an ester, right? So it could be like thought about, okay, well, there is the part that almost look like an acid, right? And then there is a part which is just kind of some alkyl chain attached, like methyl, isopropyl, whatever, right? You should be able to recall things that we have just seen, right, today. So now from the like what's it, synthesis perspective, it's gonna be different, right? So just like, for example, let's say, I don't know, like you go to, for example, Stop and Shop and you buy like blackberries and avocados, right? So, and then it can be like bought with like money, right? And money can be like cash or credit, but it's still like $20 that you pay maybe for the set of blackberries and avocados. So same with the esters, right? So we thought about that, okay, well, some parts come from the, what's it called, for example, acid, right? And then other things arrive from the like alkyl part, right? So let's say, like according to Gabriella, we'll use this acid, or Bryant was using the same acid. Everybody's using the same like benzoic acid. So that is going to be our, let's say, ester, right? So it's going to be like this, like with isopropyl. Okay, we can see, okay, well, this is almost looking like an acid, right? So without H. And this is our like alkyl part. Okay, very good. So, but how they were made? So apparently to make them, you need to use the acid and alcohol, right? So that is going to be your general example. Two words, acid and alcohol will yield an ester, right? So now let's try to see what kind of like acid and alcohol we used here. So apparently if you start, let's say like left to right, so you have ethanoic acid plus alcohol, right? So what you're going to pay attention to is that the water will be eliminated, right? So just take a look at your acid here. So that's the one. So, and then the alcohol, right? So acid will give away OH according to the like experiments. And then the alcohol will give away H. So together you will have minus H2O, right? So, and now, so I'm going to use a different color here, attention. So it's going to be red. Electron will be kind of free, right? So available electron for, guess what? The formation of the covalent bond. And then we'll have another maybe let's make it blue, for example. Blue electron on the oxygen, right? So now, so it's of course not shown here, so it kind of is bad, but if you imagine that, so we used to have now we're going to make the carbon oxygen bond, right? So let's try to do our best to make it. So that's the one. So with the black arrow, so that's the carbon oxygen bond I'm talking about, right? So it will have the red electron on the carbon and the blue electron on the oxygen, right? And then they will make a bond. So that's it. So that's your carbon oxygen bond. So now let's take a look at what happened here, right? So like potentially, how do we make this ester, right? So now we're going to think backwards. So it's kind of like retro analysis, as they call it. So if I told you, according to the example, we are going to have this carbon oxygen bond. I'm going to even use the same colors because I can. So let's see. Okay, so it's going to be red on the carbon and also blue on the oxygen, right? So this bond is made. So to make it, we need to like first break it, right? And then produce the respective parts, right? So whatever was here up to the carbonyl, right, in our example, that came from the acetic acid. Let's make it maybe, I don't know, like yellow part, right? So that's your yellow part right there, right? So then we also have the purple part, so which came from the oxygen, I mean from the alcohol, sorry. So that's your purple part right here. So all right, so now let's see what happens. So we have the parts, right? So we have basically our acid part. So circle it like that. You need to always like look at this kind of like single bond right here. That's your tricky part. And then you have the alcoholic piece right here. So now let's make the acid from the bigger red circle. So can we make it? So yes, we can do that. So we'll just be going kind of like right to left, right? Okay, in this kind of like Middle Eastern way, so to speak, and that's what will happen. So we have carbonyl oxygen. So now what is missing? So you just need to literally show the missing part to make it an acid. That's all, right? So that's what was missing. So, and you see it's kind of congruent with our writing. So the acid obtained, the acid gave away OH, right? So kind of like in this reaction, that's how it happens, right? So the acid will have to lose OH, but not because like rules change about acids and bases. That's not the case here. So it's going to be only in this particular case, right, when the acids happen to lose OH. So that's just how it works, right? So, but it's just a different scenario, right? So now finally we need to make our alcohol. So let's try to do that. So we have this isopropyl piece. Okay, very good, right? So then we have our oxygen. And now the only thing that's missing is going to be the hydrogen, right? So let's make it purple. And now if you double check, right? So check yourself. As they say in New York, so you are going to circle your water, right? So H2O will be eliminated. So basically we decided, so it was actually established by experiments that acid will lose OH and then the alcohol will lose H. So in this particular scenario, right? So don't just confuse yourself with the like acid versus base definitions. So and then here we go, right? So we make the acid lose OH, alcohol will lose hydrogen, like water will be eliminated. So we can just show it here in purple. So like plus like H2O or HOH. So same thing. And now connect, right? To make your connection. So that's your red electron from the carbon and then the blue electron from the oxygen. So together they will make, guess what, a covalent bond, right? So from the sharing of two electrons. And then, yeah, we'll be in a good shape here. We'll make our ester. So that's the esterification process. So it's also called like Fischer esterification. That's pretty much kind of like the name that we need to remember for now. And I think at this point, so like we'll continue like with more practice on Tuesday. There will be the practice session as well. And I'm gonna launch the exits exit ticket, right? So it's on Google Drive. So just a little bit of the reflections. So let's see. Yeah, that one. So it's called exit ticket. So if you want, you can reply just to kind of like whatever you want to share, you can share. If you did the partial credit, go ahead and sign up for the grade. Bye, everyone. Enjoy the cats. Okay. I was just wondering,